Welcome back. In this session, we introduce the first application of first-order ordinary differential equations, more specifically to problems in cooling. So the first problem in cooling is the application of differential equations to Newton's law of cooling. So first we state Newton's law of cooling and then solve the model that defines the cooling of a body. Thereafter, we'll do an example to illustrate how the model works. So this law states that the rate at which the temperature of a body changes is proportional to the difference between the temperature of the body and constant temperature surrounding the body. So the rate at which the temperature T of a body changes in a cooling body is proportional to the difference between the temperature of the body and the constant temperature so a Ts of the surrounding medium. This situation is represented by the first ordinary differential equation dt T is given by K into T minus Ts. So T at 0 is given by T naught, where T naught is the initial temperature of the body K is a constant of proportionality. So note that some people use negative K, some positive K, but at the end of the day, they're not the same. So let's see how we get the solution of this equation. The equation dt equals to K into T minus Ts is separable. Therefore, we solve it by method of separation of variables. That is, so we write this one as dt divided by t minus ts equals to k dt. So just dividing through by t minus ts and multiplying both sides by dt. So integrating both sides, that is integral dt over t minus ts. Remember, ts is a constant. Integral of k dt gives, this will be ln of t minus ts equals to kt plus a constant of integration c. That is, if you exponentiate both sides, t minus ts be given by e raised power kt plus c, which can be written as e raised power c, e raised power k t, and this can be written as c1 e raised power kt, where c1 is e raised power c. So which implies that t minus ts is c1 e raised power k t, or t is given by c1 e raised power kt, then plus ts. So applying, so remember this is t of t. So this is the same thing as writing capital T of t is given by c1 or ts plus c1 e raised power kt. Now applying the initial conditions, t at 0 will be same as ts plus c1 e raised power k times 0. This should be t naught. This implies ts plus c1 equals to t naught. So which means c1 is t naught minus ts. So therefore, the solution of the equation is capital T of t is given by t naught minus ts, the value of c1, e raised power kt plus ts. So the solution of that equation. So notice that if this constant is negative, then limit as t approaches infinity of e raised power kt equals to 0 and limit as t approaches infinity of t s will be ts. So the temperature of the body approaches that of its surrounding. Actually, this is once we have this, actually this is the T of T. Because immediately now you say this is 0, so this part will be, this will be 0. So T of T will just actually be Ts, its surrounding. So which means then we can do an example to illustrate how this method works, or how the Newton law of cooling is applied. So example, the normal body temperature of most healthy people is about 98.6 degrees Fahrenheit. Suppose that when a body is discovered, at noon, its temperature is 82 degrees Fahrenheit. 2 hours later, its temperature is 72 degrees Fahrenheit. If the surrounding is 65 degrees Fahrenheit, find approximate time of death. So this is a good problem in the application of Newton's law of cooling. Now to solve this, I will say let T of T denote the temperature of the body at time T, where T of 0 represents the temperature of the body when it was discovered, and T of 2 represents the temperature of the body 2 hours after it was discovered. All that information is given in the question. So in this case, we have, so remember by definition, our Newton law of cooling is given by dt equals to k T minus Ts. T at 0 is given by T naught. This is the model that describes that situation. So here we have T naught is given as 82, that's the initial temperature of the body. So this is given. And Ts, temperature of the surrounding, is given as 65. And then we say that the solution of this equation is given by T equals to T naught minus Ts e raised power k T plus Ts. This is what we obtain after solving the Newton's law of cooling model. If you don't remember that solution, then the key thing to remember is the model itself, and then you can always use separation of variables to solve this equation with these initial conditions. So with what we have, then it means that our T of T is given by 82 minus 65 e raised power kt plus 65, which will give us 17 e raised power kt plus 65. Now, using that after 2 hours, the body of the temperature of the body was 72 degrees Fahrenheit. So T of 2 is 72. And we have said that T of T from this is given by 65 plus 17 e raised power kt. So this implies T of 2 is 65 plus 17 e raised power 2k should give us 72. So this means 17 e raised power 2k is the same as 72 minus 65, which is 7. So which means that e raised power 2k is nothing but 7 over 17. So this can be written as e raised power, okay, so introducing ln on both sides, so this means that 2k is the same as ln of 7 over 17. So that now we get k to be a half ln of 7 over 17. So therefore the model is T of T is given by 17 e raised power a half ln of 7 over 17, this is the value of k, times t plus 65. So we have been told that the normal body temperature is 98.6. So when the temperature is 98.6, then this when someone is alive and healthy. So we'll have what is T. So 17 e raised power half ln of 7 over 17 T plus 65 should give us 98.6. So 17 e raised power half ln of 7 over 17 times T should be 98 minus 65, 98.6 minus 65, which is at 3.6. So e raised power a half ln of 7 over 17 T is the same as 3.6 divided by 17, which is 168 over 1445. Then introducing ln on both sides, we'll have a half ln of 7 over 17 T equals to ln of 168 over 1445. Now, ln of this answer, this is the same as a half, which is 0.5. So first, 7 divided 17, ln of answer times 0.5, I get negative 0.443651597 T equals to, now ln, so 168 divided by 14.5, ln of answer, so negative 2.151900621, which means T is negative 2.151900621 over negative 0.4436597. So divide negative 0.44365159.7. So this, but they so that we don't get this negative, so we can as well just multiply through by 2. So we'll have ln of 7 over 17 T equals to twice ln of 168 over 1445, and then the same as ln of 7 minus ln of 17 T equals to twice ln of, this point here where we had that 3 over 17, let's just see, that 3.6 divided by 17. That 3.6 divided by 17 is 168 over 85. So this is not 14. This is 168 over 85. So this is 85. So we have 2 into ln is 85, 168 minus ln of 85. So it means t will be twice into ln of 168 minus ln of 85 divided by ln of 7 minus ln of 17. So ln of 168 minus ln of 85 times 2 divided by ln of 7 minus ln of 17 gives us negative 1.5, 1.535693,158. So this means that, so remember this time is in hours. The time of death occurred approximately 1.536 hours before the body was discovered. I remember this is the same as 1 hour. And then so 0.536 times 60, roughly those are 32 minutes. So which means time of death is approximately so we had 12, we subtract 1 hour 32 minutes, so 60 minutes, so we have 8, 2, and then 11, this is 10. So 10:28 a.m. since the body was discovered at noon. So that's how we solve that problem. Thank you.